Okay, I want to run through one complete example. Actually, we're going to do two complete examples. One for means and one for proportions. And those formulas are going to be a little bit different than before, but I think you'll be okay. So here it's talking about, we've got a lake where there's some fish. We take a random sample of 10 fish from the lake. We've actually used this data before. And now we're going to say, is there sufficient evidence to conclude the mean PCB concentration for a fish exceeds 5 parts per billion? So this is a problem involving means. So notice I wrote mu, the population mean PCB level. That's unknown, because that means we're doing inference. And then I wrote the null hypothesis is mu equals 5. Okay, it's always mu. These symbols are always the same. It's always an equals for the null hypothesis. And then why did I get to 5? Well, we think it's 5, right? If everything was good, it would be 5, and that would be okay. Our alternative hypothesis is, oh no, we think the fish are unsafe, so that's mu is greater than 5. And notice that once you can get the equals part here, then the only decision to make here is this a less than or a greater than or not equal to? Well, the exceeds here, and then kind of the unsafe if it exceeds indicates to you it's a greater than. One little wrinkle that's going to come up on this question is on the first example I did, we actually knew sigma. Well, in this example, we don't. We know S, or we don't know S, but we can certainly calculate S from all those numbers, right? So here, on the previous example, we used a Z test. Well, just like on confidence intervals, remember we started doing a Z interval, and then I said we're never going to use that again because it's unrealistic that you actually know sigma. Well, same thing's going to go on here. We're actually in this one using a T test. Everything I told you before is the same, which is going to be a slightly different formula using S instead of sigma. So let's move on. Oh, gee, that's weird. Look, my picture's in the wrong place. See if I can correct that. I'm not sure I can. Well, oh well, that's awful. Anyways, the conditions are exactly the same. We'll assume the 10 fish are a simple random sample. Now we're doing a t-distribution, so I wrote since n equals 10, the t-distribution is only appropriate if the sample distribution is more or less symmetric and unimodal, because our n is only 10. We can only use the t-distribution if it's like 30. Well, it turns out here I made a little box plot, and you can see that actually it's more or less symmetric and unimodal, which means that's, thank goodness, we can use the t-distribution. And then we'll assume independence because there's at least 100 fish. Same conditions as before. Again, we're doing a t-distribution here, so this was a little bit wordier. Okay, now here's the formula, and I want to just highlight this right away. Notice this formula is a little bit different than what I wrote in the first example. It's t instead of z, and here it's t because it's s here rather than sigma. Everything else sort of stays the same, though. I calculated x bar and s. I did this just using one var stats. Okay, and then I'm basically saying here's x bar minus what we think mu is over s divided by the square root of 10. We get a t-score of 1.66. And then down here, this is the t curve with 9 degrees of freedom. Remember, degrees of freedom is just n minus 1. So obviously 0 is in the middle, 1.66 is over here. So if I shade to the right, I get a p-value of about 6.4%. And again, this is the key number in this question. This is the answer, if you will. There's about a 6.4% chance of getting an x bar of 5.55 if we think that mu is actually 5. That's what that number actually means. So would you say this event is unusual? Well, if our cutoff is 5%, we would say it's actually not that unusual to get these fish, right? Because it's going to happen about 6.4% of the time, and our cutoff for unusual is 5%. And that idea is exactly what I wrote on this page. So this is step 4 of the inference toolbox. I copied this box here, a little bit crooked, I noticed. So I wanted to kind of match up this box to what I wrote over here. There's about a 6.4% chance, that's the p-value, of getting an x bar of 5.5 or more. That's exactly this part right here, due to random variation. If mu is actually 5. I guess I should wrote that in. It's not quite the same. Since this is unlikely, so look, I picked the first thing. I picked unlikely here. Oh, sorry, I take that back. I did not pick unlikely. I picked likely. Rewind in time. I picked likely, right, because this number is above 5%. So because this is likely, now I'm going to pick the second thing in each thing. We will fail to reject the null hypothesis. There is not evidence that the mean PCB level is too high. Okay? And this is like a beautiful answer. The p-value kind of determines exactly what you write there. Okay? That's a complete example. I hope the fact that it was t instead of z did not mess you up a little bit. Just to kind of highlight that difference a little bit, I have written the kind of 4 key formulas here. The first one in red, this is the general formula that you'll use for all hypothesis tests throughout the remainder of the year. This formula in purple was the one I used in the first example. This is the one we're actually not going to use too much anymore, because you only would use this one if you happen to know sigma, which we talked about last chapter is very unrealistic. The one in green is the one we just used. Okay, it's called a t-test, and again the only difference is it's z instead of t, and it's it's s instead of sigma. T instead of z, s instead of sigma. This is the one we'll use a lot for means from now on, right? And then we haven't done one yet, but actually you can do hypothesis testing for proportions, and this is the formula we would use for proportions. And then we go back to z. The statistic is p hat, the parameter is p, and the standard deviation of the sampling distribution is square root of pq over n, which should look familiar to you from last chapter. Okay, this kind of follows our rule from chapter 10 that you use t whenever you're talking about means and z whenever you're talking about proportions. Now I want to do an example involving proportions. So it says, an experiment on side effects of pain relievers assigned arthritis patients to one of several over-the-counter pain medications. Of the 440 patients who took one brand of pain reliever, 23% suffered some symptoms. Does this experiment provide strong evidence that fewer than 10% of patients who take this medicine have symptoms? Perform an appropriate test. Well, at least in this case, the problem gives you a hint to do a test because they use the word test here. But again, notice that kind of idea of strong evidence. So a little bit different here, but we're still going to follow the inference toolbox. Our parameter now is p instead of mu. That's because this question involves proportions, right? And kind of what's that clue? Well, first of all, we're talking about a percent here, right? And then we're talking about 23 out of 440. That indicates the idea of a proportion. So now our null hypothesis, which used to always be mu equals, is now p equals. Again, these symbols have to match. Okay, so we think p is 10%. That's what we're kind of testing. And our alternative hypothesis, again, same symbol, same number. The only difference here is what goes in the middle. And notice we're saying fewer up here. So our alternative hypothesis is p is less than 10%. If everything was being good, we suppose that p is 10%, but we think that we're testing that it's less than 10%. Okay, now going on to step 2, the conditions. Exactly the same idea as if we were doing it as a confidence interval. So we'll assume that the 440 people are in SRS. We check NP is greater than 10 and Q is greater than 10. And therefore we can approximate the sampling distribution of p hat as normal. Since there are more than 440 times 10 patients, I guess in the world, arthritis patients, we'll assume that their responses are independent. Step exactly the same as we were doing for confidence intervals. Okay, now step 3, the calculations. Here's our new formula. Z equals p hat minus p over the square root of pq over n. P, going back from step 1 of the inference toolbox, is 10%. P hat, we just calculate, is 23 over 440, which is a pretty small number. It's like 5.23%. Then we crank out all the numbers, right? Here's p hat, here's p, here's the square root of pq over n. We get a z-score of negative 3.337. So then if I draw this, you can see that, I hope I did this right on the next page, I'm just blanking out here. We get a z-score of, negative 3.33. Okay, the p-value would be if you'd shade to the right here, or sorry, shade to the left over here. That's an unbelievably small number, right? It's about, 0.0004, right? Really, really unlikely. And what's hard about it is this, I noticed I made the distinction, right? P-value here, and then p and p hat here. There's just lots of p's going on in the question, right? This p means that what we think is true about the population proportion. This p hat is the sample proportion. The p-value, though, means something very different. This is a probability of getting this p hat if this proportion, if this p is true. The p-value is the probability of getting the statistic if the parameter you think is true. Confusing because there's lots of p's. Okay, so now we write our paragraph, and I included a little thing down here again. There's a very, very small chance of getting a p hat of 23 over 440 or less due to random variation if p is actually 10%. That's kind of this first sentence here, right? Just plugging in. Now we pick the first thing in each thing. Since this is very unlikely, that's the first thing I wrote down here, we will reject the null hypothesis. That's the first thing I wrote down here. There is strong evidence, I said strong evidence here because it was so unlikely, but we picked the is here, there's the is there, that the proportion of those who have symptoms is less than 10%. That's what we wrote as our alternative hypothesis. Remember, our alternative hypothesis was p is less than 0.1. Notice this part right here is exactly what I wrote as my alternative hypothesis, but here it's kind of in English, where in step 1 it was symbolic. That's a complete example. Just very quickly, I wanted to show you how to do these problems on the calculator. I wasn't actually cranking out all those numbers in the calculator. You can go to on your calculator to the stat test menu. In here, the first first 6 things are all hypothesis tests. The next 6 or so things are all confidence intervals. So this time we were doing a t-test, that's number 2. We had data, which I put in L1. Notice right here, this mu0 is the mu of our null hypothesis. In other words, when we wrote down the null hypothesis, we thought that mu was 5. So this number 5 is what you're writing right there. Okay. Then notice it's our alternative hypothesis. And by the way, this is in L1. Our alternative hypothesis was mu is greater than 5. So notice this, there's my pen color here. This greater than symbol is what goes right there. This little box right here, this actually says calculate. And if you calculate it, you're going to get a screen like this. Okay. Notice it tells you the t-score, which we wrote on the previous, when you did the whole problem. This p-value is the key thing. Remember the 6.4%? That's where it comes from. Okay? I don't know why I think the S is the wrong thing. Maybe I picked the wrong number somehow. And then actually, if you instead of you clicking calculate here, you pick draw, it actually draws you this whole curve and gives you the 2 really important numbers, which are just the t and the p. This might actually help you draw the curve, which is a good thing to do in these questions. And notice this is actually a t curve, not a normal curve. You know, they look very similar. Just quickly to show you, this is for the second question. Okay, we're going to go to one prop z-test. Okay, so the 2 things we're going to use in sections 11.1 and 11.2 are number 2, which is a t-test, and number 5, which is a one prop z-test. Those very much correspond to their counterparts down here, which were 8 and a, I believe, for confidence intervals. Okay. Well, when we did this question, we wrote down HOP is 0.10. That number 10% actually is going right here. It's what they're calling P sub 0. Then X and N, that kind of calculates P hat. Then when we wrote our alternative hypothesis, we wrote P is less than 10%. So notice that this less than symbol right here is what goes right there. And now here you can see the 2 buttons that were obscure last time, calculate and draw. If you pick calculate, you get a screen like this. And notice it tells you here's our z-score, we got that before. Our p-value is unbelievably small. And then it actually shows you your p-hat also. Okay, if you picked draw up here, it would draw you this curve. Now, it's not actually showing any shading because the shading is so small over here you can't see it. But it does give you the 2 critical numbers, the test statistic, the z-score, and the p-value. There's a lot of information on hypothesis tests. We'll get a lot of practice with this and do a lot of examples, but it does kind of I ran through 3 complete examples. And you'll get it, trust me, you'll get a lot of practice with this as time goes on. And that wraps up section 11.1 and section 11.2, and that's it.